Hello all, I am Vignesh, working as an assistant professor in the Department of ECE at Kongi Engineering College. So today's topic is about acceptance angle and numerical aperture. So recent days, the number of users those who are accessing the internet are increasing exponentially. So in order to meet the demands of such huge users, we need a higher bandwidth, low loss, less delay and increased speed. So fiber optic communication is one of the communication which will satisfy all of this requirement. So we know that the basic principle behind the light propagation inside an optical fiber. So optical fiber is a medium which is used to carry the information. In fiber optic cable, in the fiber optic communication, the informations are carried in the form of the light signals. So the principle behind the light propagation inside the optical fiber is total internal reflection. You have studied these basic concepts in the elementary school level in your basic physics. So there are two conditions which are need to be satisfied for the light propagation inside the optical fiber cable for the total internal reflection. The first one is the light should travel from the denser medium to rarer medium. Another one is the incident angle should be greater than the critical angle. So now the question arises. So consider this is a fiber optic cable. The fiber optic cable consists of three layers. One is the core, which is having the higher refractive index. We call it as N1. Another one is the cladding, which is having slightly lower refractive index than the core. We call it as N2. Then we have an outer layer, we call it as a buffer jacket to protect the fiber optic cable against the environmental condition. Now the question is whether the light incidenting on this fiber optic cable at any arbitrary angle can be propagated inside the fiber optic cable or not. We are going to answer this question through this derivation. So let us consider this is the fiber axis. So the center of the core, we are drawing one line. We call it as a fiber axis. Now let us say the ray, light ray, this is considered to be a light ray. Let us call it as A, which is incidenting on the fiber axis with the angle theta naught. We call it a incident angle as theta naught. So now this line which separates the air from the fiber optic medium. There are two medium. Left side, you consider this line, left to this line we have a air and right to this line we have a fiber optic medium. So now you need to draw the perpendicular line to this boundary line. This is called as boundary line because it is separating the two medium. One is air, another one is a fiber optic cable. Now the normal to the boundary, normal to this boundary line, we need to draw the perpendicular line. So at this perpendicular line, your light ray making one angle, we call it as a theta naught, which is considered to be as incident angle. Now let us call the refractive index of a core as N1 and the refractive index of a air as N0. Now according to the Snell's law, which you studied in your basic physics, we are going to write the expression. Now you look at this boundary line. So this is the incident ray. So in this left hand side you will be having the refractive index N0 and the incident angle is theta naught. So N0 sin theta naught. Now since the light propagating from the rarer medium to denser medium, the light ray will bend towards the normal. So and it is making the angle of theta 1. So according to the Snell's law, can write N0 sin theta naught, it should be equal to N1 sin theta 1. Now here also you are inside the optical fiber cable, you are having two medium. One is a core which is having the refractive index N1. Another one is a cladding which is having the refractive index of N2. Now this is the boundary line which is separating the core and the cladding. Now I am going to draw the normal line perpendicular to this particular boundary. And this particular light ray A, which is making the angle, let us call it as a theta C. Actually whenever this theta C is a critical angle, when the incident angle is greater than the critical angle, the light will be total internally reflected and it will be propagated inside the optical fiber cable. So now I am considering the marginal condition. I am calling it as theta C. Now you consider this triangle. I am naming it as, for example, O, M, N. I am taking this triangle O, M and N. From this we can see that this is making the angle of 90 degrees, and this angle we know it is theta 1, and this angle we know which is theta C. Now you need to add all these three angles. We know that sum of all the three angles in the triangle which should be equal to 180 degree. So theta 1 plus 90 degree plus theta C, this should be equal to 180 degree. I can bring this 90 degree to the right hand side. So theta 1 plus theta C, which should be equal to 90 degree. Now from this I can write theta 1 equal to 90 minus theta C. So this is the expression I am having right now. Now I am going to substitute the value of theta 1 in this expression. So what is the value of N0? N0 is the refractive index of the air. So the value of refractive index of air is 1. So sine theta naught N1. Instead of theta 1 I can substitute this value. So sine of 90 minus theta C. So this should be equal to N1 cos theta C. So this expression I can write it as, cos can be written as 1 minus sine square theta C. Now this again can be written as 1 minus the value of sine theta C, the critical angle value can write it as N2 divided by N1 square. Okay. Then N1 square root of N1 square minus N2 square divided by N1 square. Then this can be written as N1 divided by N1. The square root of N1 square will become N1. That term I am bringing it to the denominator, square root of N1 square minus N2 square. Now this is sine theta naught. Since it is incidenting on the normal line, taking it as theta A, where A stands for the acceptance angle. Now I am taking another ray. Let us name it as B. From this figure I can see that, suppose I am taking this angle as theta naught dash, then from this figure I can say that theta naught dash is greater than theta naught. You refer this expression here, N0 is fixed, N1 is fixed. The only changes happening in the sine theta naught. So if theta naught increases, then obviously the value of theta 1 also increases. So theta 1 dash also greater than theta 1. Now you see this expression. From this particular expression, is naming it as star. From this expression, theta C is nothing but 90 minus theta 1. If theta 1 is very large, if theta 1 dash is very large as compared to the theta 1, then obviously the new angle theta C decreases. If the critical angle decreases, then obviously the light will not be propagated inside the optical fiber, because the condition for the total internal reflection is that the incident angle should be greater than the critical angle, but here the critical angle itself decreases, so the light cannot be propagated inside the optical fiber, rather it will propagate to the cladding medium and it will be lost. Now from this we can say that not all the rays which are inciding on the fiber optic cable are propagated inside the optical fiber. Up to certain angles, we call it as theta naught, light can incident from this side as well. So this entire area I am calling it as acceptance cone. Means what are all the light which are inciding on the acceptance cone, that will be propagated inside the optical fiber. Now the acceptance angle is nothing but the maximum angle relative to the core axis through which the light ray can be propagated inside the fiber optic medium. Okay, Then what is a numerical aperture? So this is called a numerical aperture, that is the sign of acceptance angle, we call it as a numerical aperture. Then from this we can calculate the acceptance angle as well. So theta A is nothing but sine inverse of numerical aperture or sine inverse of square root of n1 square minus n2 square. So numerical aperture is the light collecting ability of an optical fiber. So this is the explanation about the numerical aperture and the acceptance angle of the optical fiber.